Okay, so let's see, logistics, well, I just already told you this, but we have a class website, no Canvas. Make sure you're on Gradescope and Piazza. I know some people joined late, that's totally fine. This week, so you have a homework assignment due Tuesday of next week. Normally, we have for your pre-lab is due before you start lab, except for this week. It's a kind of a light lab anyways. And there's lots of people coming in and out of the class, so we just decided to make it easy, and all the pre-labs are due at the same time the in-lab and post-lab is, but only for lab 1. Let's see, I have office hours Thursday from 3 to 4 or by appointment, and I'm happy to give anybody who wants the analog tutorial. And I don't mean analog circuits in the way of like, oh my gosh, I have to calculate things. That's not going to help you in this class. I'm just trying to give you the intuition of when you see voltage symbol and a switch and a resistor, what's going to happen when you close that switch. That's the sort of knowledge I need you to have to get through a lot of the project, but also some serial bus stuff and this generally labs or LEDs in your lab. So the analog part is just enough to get you through the class, but there's no like calculations. All right, any other logistics questions? Oh, I just asked this question. Okay. I also this year wanted to do like a component of the day because so embedded systems like other classes like 370 is completely contained. All of the content you need for that class, they've made up an ISA for you. It's all in that class. But embedded systems is not like this. You're taking a part of a subject matter that's really, really large and distributed throughout the industry. And so if depending on your background, you might have done Arduinos and stuff, already know a lot about embedded systems, or you might be your first time. And so to be successful like in lab and make it easier for yourself and also be successful in the projects, you need to take from these other little areas of knowledge. So I'm just going to fill it in for you. You can just turn off your brain for a second if you're not interested, that's fine, but just kind of general concepts in the beginning. So there are things called header pins and connectors, and they are ways in which you can connect peripherals to your PCB board. So you have header pins that you were probably probing in your labs, and so you could have, instead of taking wires and connecting directly, you could have a jumper cable or something like that, or some mechanical way to do that. So the industry has filled out any number of ways to mechanically connect wires together. There are some important things. When you get to batteries, you want to make sure that you're not doing it backwards. So when I was at Disney, I mentored, we had a relationship with ETH Zurich, we had a lab there in Switzerland, and so I was mentoring a PhD student, and she was a computer scientist working on embedded systems and no other embedded systems people there. And one of my favorite people to work with, but she was also famous for lighting things on fire, okay? And so there's a famous time when she was working on this body-coupled technology, which let you transmit things through touch. And they had a magic floor that you would walk on and would light up. And the executive from Disney, I think a VP from Imagineering, came through and wanted to see the demo. And she's famous because she plugged her thing in and all of a sudden the floor caught on fire. Okay? Why did that happen? Well, at the time she was just using normal header pins like this to connect her batteries. And this big beefy battery. And what she didn't do is she was a little nervous and she put it in backwards. So now you took power and shorted it directly to the ground and something caught on fire. So if you use the right connectors, so there's this idea of connectors that are keyed in the sense that they can only go in one direction. Right? You cannot physically insert them backwards, and locking, which means they won't jiggle apart. So anyways, not important to your grades in this class, but just a practical thing. When you're connecting things, make sure people have already thought about all the proper ways to do it, and you can take advantage of all that knowledge if you're trying to connect batteries or boards together. Any questions? Okay. And if you get real excited and want to learn a whole lot about headers, you can follow that link. Okay. So from last class, we talked about what's embedded systems, we did class overview, and we did high-level kind of architecture of how you would write code and how the core would manipulate GPIO. The goal for the next, say, 3 weeks is to understand how code, the registers in the core, and memory work together, and eventually how they manipulate those registers on a more detailed level and how you communicate with the outside world. So today we're really going to be working on the ISA, understanding that so that we can start using all these pieces together and understanding how the ARM Cortex M4 that you have in lab works. All right, so today we'll do a little background on ARM, talk about instruction sets, instructions themselves, and then we'll have an indexing problem. All right, so to understand why the chip is set up the way it is, to understand why the ISA is set up how it is, it's important to kind of understand ARM's business model. How do they make money impacts dramatically the type of thing that you have to work on in this class. So ARM is a fabless semiconductor company. Does anybody know what that means?
They sell their designs to manufacturers to produce?
Exactly. They don't actually make chips. So you have a dev kit that says ARM Cortex-M4 on it, or a chip, but they didn't make it. What they do is they design the ISA, so the architecture, the instruction sets, and they sell intellectual property. So they may have like a bus structure that works really well with their system. They'll sell you that, or an ADC possibly. But they define the architecture and the instruction sets, and then what they do is they license that to chip manufacturers. So who would that be? So Cypress, STM, NXP, Apple, Samsung. These people use this information. So why not just roll your own? Why don't they all just make their own processors? It's really hard, and it's hard to get right. Right? And so the cost of having small bugs, as we think back to probably before you were born, Intel had a 386 processor that some of the MOSFETs just weren't quite big enough. And the problem was that when you're doing some calculations, the numbers didn't turn out right in random times. And it's just because it takes time to get these things correct. So they licensed the technology, and then what did they do? So Apple or Texas Instruments or Cypress, they'll go and add some extra technology because they don't want to just all sell exactly the same thing. So for instance, Cypress Semiconductor, they were really big into LCD screens. So they would make drivers, which were peripherals, so hardware components that made it really easy to interact with LCD screens. And then the programmers, all they really had to do was know ARM. They had to know a little bit about what Cypress did to make interfacing with those LCD screens simple, right? But that means that if you know this, now you get to work at all those companies, or all the companies that possibly sell ARM.
Is that also the case for like some 1 of 2 and 3 chips for Apple?
Yeah.
Is it also by ARM?
Yes. Now, Apple being a large company added their own special sauce to it, right? So it's not just like the vanilla ARM. Like when you get like the small microcontrollers, the companies aren't modifying it that much because it's not that profitable. But for Apple, right, they made major modifications to probably ARM in some way. I don't know all the details. Any other questions? Okay. All right, so understanding that they don't make the chips themselves, they just make an instruction set. And remember, this has to be compatible with all these manufacturers, right? So that's going to impose some design considerations because you're not going to make a special SKU just for NXP and a special one for Cypress. So much to keep track of from a business point of view. They want one set of specs that will work for everyone. Of course, that's not technically possible to have one ISA, so they have different families. So they have the application class processors. So that's anything basically with the user interface and a screen. So Apple would be an example of an application class processor. It's the Snapdragon family, all those are ARMs. Then you have the real-time family, which is real-time in the sense that there's some hard guarantees about reliability, essentially. So you see that in automotive and avionics. And then we're looking here at the Cortex-M family, which stands for microcontroller. So they're not application class processors. They're much smaller. They're more cost-sensitive, lower power, much lower power than other things. And so it's also important to understand the difference between instruction sets, which are down here, and chip architectures, which are up there, okay? So, for instance, here we have the application class processors. We have the mobile versions. You can have multiple instruction sets able to be compiled for a particular processor. So it's just important when you go out and you're trying to look online for information because this class is confusing, you just need to look at something, you have to make sure you're looking at exactly the right architecture and the right instruction set, or else you're going to have information that's just not relevant. And this is really hard and opaque to understand if you're starting out. So specifically, we're looking at ARM V7M and Thumb 2 instructions, yeah.
That chip architecture be compatible with more than one instruction set?
Yes. So for instance, these ARM v6s here have all these instructions, right? In fact, you can have an instruction set like all of those processors are compatible with the ARM 32-bit ISA. So there's inner compatibility. It's just opaque and not clear. Like you start out, it's really hard to keep track. So just make sure that when you're looking for documentation, you're looking for exactly the right thing. Did you have questions? Okay. All right, so what is an instruction set? So an instruction set architecture is an abstract model of the computer. It defines how software controls the CPU, and essentially it's an agreement between the programmer and the hardware designer that says, if you write these instructions, if you use these instructions, they will do exactly something. But how it gets implemented is the hardware side, right? You can have different architectures implementing a set of instructions. That's up to the hardware manufacturer, but it's the programmer, there's the agreement between the two. So the ISA defines instructions, data types, data storage, addressing schema, data flow control. So all the things that you would need to run a processor. So for instance, here's some examples. There's the thumb 16-bit ISA, or the ARM 32-bit. I don't know if this is true, but it's supposed to be here's the ARM is bigger than the thumb. I have no idea if that's true. That's what the old faculty tell me. I'm going to believe them. And so there's optimizations here. So a 32-bit instruction set is more expressive, right? You can, in those 32 bits, you can get more done. You can do maybe an add and a multiply together, right? You can have it address more memory space than you can have with a 16-bit, but it's going to take up more space. Your program space is going to be larger. So there's an advantage of having 16-bit instructions for code size. In this class, well, not for this class, but in this class, we're going to study the Thumb 2 ISA, which is a mix of both 16 and 32-bit instructions, which ARM claims outperforms everything. Of course they do, that's marketing. But they're going to say that here we're going to get the best of code size and speed by optimizing which instructions are going to be in their ISA. If you go look at the Thumb 2 instruction set, and you look at the processor's architecture, chip architectures that support it, you'll see that there's Cortex M0, M3, M4, there's even M4F. And basically, they're all, each processor, as the number goes up, becomes more complicated and supports more and more instructions. So the Cortex M4 has floating point support. So basically, you can see this as like an onion where you get more and more, the more layers you have, the more instructions you have, but you're always backwards compatible. All right. So what am I trying to say? Oh, okay. So the chip architecture defines how the ISA will process hardware, right? So instructions. And so, so here's an example. You have multiple variants of the Cortex M4 using the MVR structure. But so here, consider this. So you can have, so let me rephrase this. Instructions can work on multiple processor architecture. For example, the Cortex A8 is an application class processor. It can do Thumb 2, and it's a 13-stage processor versus ours, which is a three-stage processor. So you put that together, they can both run the same instructions. It's just that each architecture chooses to implement them in a different way. So if you write code for this, it will work on all of those. All right, so here's a question for you guys. So what technology trends are causing, or did cause, not necessarily specifically for microcontrollers, but as processors, we developed more and more. We started out with like 8-bit, then 16, then 32, then 64. What is causing this trend, or what technology is causing us to have the shift from 16 to wider and wider processors? And likewise, how is this impacting microcontrollers? So think about the industry in general. Take 60 seconds to talk amongst yourself. Why have we increased the number of bits in our processors, and how did that affect microcontrollers?
Integers and 64-bit floating point numbers. I don't know. Memory's also just a lot cheaper. Yeah. You can change the sensitivity. Architecture is still a 32-bit instruction, right? 16-bit. 2-bit. I'll show you all power constraints.
Yeah, it's gonna be a lot slower.
Switch all these transistors.
Exactly.
I think it's a lot more.
Yeah, like we can actually have registers that are 64 bits, whereas before it was hard to predict.
All right, so let's answer the first question. Why do you, so if we think about just, desktop application processors, for example, what has caused a shift from like 32 to 64? Why did the industry do this?
Memory is getting a lot cheaper, and so we can, with the 64-bit, you can access a lot more memory.
Correct. So, and why is that? What's the key idea? What's the limitation of 32 bits?
Larger memory.
But there's you're both got the right ideas, but there's a little key concept. Yeah.
The instruction size and like how much is dedicated to like.
Yeah.
32 bits can only address 4 games.
That's right. So you all have the same ideas, right? But the 32 bits can only get up to 4 gigs of memory. So that means, I guess this was 2003 or so, about this time period, all of a sudden applications wanted more memory. We wanted computers that had bigger and bigger memory, but how do you get there, right? And now you're in the situation where the entire industry had to change its architecture, which was painful and miserable for everybody, because now you went to a new processor that was poorly supported by your OS. Software manufacturers weren't making software that was compatible yet. It was kind of like moving from Apple's moving from Intel architecture up to M1, and I guess Windows is doing the same thing, only they have their own ARM architecture. So you had to wait for the whole industry to get up to speed for that to happen. But it was worthwhile from a memory point of view. Okay, now we can have lots of memory. How about the second question? So that was for application class processors. What about for these little microcontrollers? What is this meant that you could have 16-bit or 32? It's a little vague. Yeah. Your name is. I'm trying so hard. Varan? What's your name? Yeah.
Conan.
What?
Conan.
Conan. Oh, I was getting close. Okay, I'm gonna get there by the end of the semester. Okay, go for it.
I think it has to be both because it has to be backwards compatible and then also like serve the new markets. So it's probably like a business decision to have it work for old things and then also serve new things.
Yep, and they don't. Yeah. Any other ideas? That's a good one. That all makes sense. Yeah.
Cloud computing.
Cloud computing. I don't think the little microcontrollers here are worried too much about cloud computing. Yeah.
Actually, since they don't have to be like programmed as much with such larger things, and they're doing really small tasks, you can just have a much smaller file size or program size to run.
Yeah. So now we're optimizing for small and energy efficiency. So to that size, keeping the 16-bit around lets you have smaller size and be more flexible, even though they could go up to 64-bit architecture, just not going to gain that much from making that big transition. So instead, ARM in general focuses on the lower, more power efficient, give up performance, but let Dennard scaling and Moore's law make those transistors more efficient. And then they'll build a hybrid ISA just to get the most they can out of that little lower end piece of silicon.
What does it mean for it to have like a hybrid 16 and 32-bit instruction? Like, is it registers are both there's some 16-bit registers and some 32-bit registers, or is it like instructions are separated?
We're going to get into that. The quick answer is that you should think about this as a 32-bit processor with registers that are 32 bits. It just means that the instructions themselves could be 16 bits, because maybe you don't have to do as much.
If the instructions varies in size, wouldn't that kind of be like the CISC instruction set?
We can all debate about what the definition is, but I would say CIS is more about I don't know. No, I don't think so. I can't debate that one with you. I can just say I don't think the industry agrees with you quite yet. All right. Those are just the answers. They'll be posted online. Okay, so let's go talk about the instruction set. We'll talk about memory, registers, and data path to kind of talk about some of the questions that just came up. So remember, this is our simplified model of the Cortex-M4 architecture. Just a reminder that all the data paths in here are 32-bit wide, which means you can transfer 32-bit words throughout it. You might have extra, these might be wider because you need to have address bits and control bits, but the data path is all 32 bits. For the context of this lecture, we only really care about the core and memory. Okay, that's all the ISA really knows about. So let's think about memory organization. So ARM has gone through and said, these are the regions, and this is what you do with those regions of memory. And they did that because they don't want to make Intel, or I guess not Intel, but say NXP a different, have code in a different spot than everywhere else. So they say, okay, I want to have all your code goes here, all your SRAM, all your peripherals go in those particular memory locations. So as we talked about, if you go for 32 bits, you can get to 4 gigs of RAM. Okay, wow, that's a lot. And in this world, it's all unified memory. So they don't make any distinction between flash. I'll talk about that. So flash is non-volatile memory, where you would put code in. Non-volatile meaning that when you power it off, the state is retained. And when you turn it back on, then you can read out of it. SRAM, on the other side, is much faster, but it loses its memory. And in this architecture, it's just an address, right? In fact, ARM doesn't really know what the manufacturer did underneath. They say, you know, put your SRAM here, sure, but you could have made this out of flash if you wanted to. It's just saying this is where memory goes, essentially. Okay. So memory regions are predefined for interoperability. Now, this is the memory map for your STM32 that you're using in lab. In fact, so here you can see we've blown up some of the sections. You have your bootloader and flash memory and SRAM, but you see a lot of these reserved signals, reserved lines. And that is ARM just saying, we haven't implemented it, okay? So ARM doesn't have 4 gigs of memory on there. That would be cool. I would like to have a microcontroller with 4 gigs of RAM. I bet I could do some cool things with it, but it's not financially practical to do it. So they have a bunch of stuff reserved, which means not implemented. In fact, so for example, the ARM v7 architecture allows for 500 megabits of SRAM. Amazing, but we only get 64K. Okay, that's what's implemented. Any questions about that? Yeah.
Does not implemented mean that ARM can go back later and implement something, or that is it for like Apple to go and implement later on?
So this is the memory map for STM.
Oh, okay.
Right? So STM will make different SKUs of processors. So some processors don't have 64. They might only have 32K. And then another company can do however or whatever size memory you want. It just could not, or SRAM, it just can't be more than 500 megabytes, which is insane. So my guess is that, you know, the architects basically said, I'm going to try to make this future-proof. Right? So I'm just going to give lots of space, even though we know nobody's probably going to use it. Any other questions? We talked about this a little bit, but the ISA treats memory as a unified block. In fact, it treats everything, like all the peripherals, all the registers and the peripherals. Those are all just memory locations, okay? So let's talk about addressing memory. So each memory location has 32-bit addresses. So here we have addresses, and here's your data that's stored in there. So each memory location holds 8 bits, but that's kind of a weird way to think about it once you kind of understand the architecture. Well, that's technically true. However, this is really a 32-bit architecture, and we do all our operations on word sizes, not byte sizes. And so the way you should think about this is really, so while this is individual addresses, so 1AC, and then you increment in 1AD, so memory is going increasing here. Those are all individual places you can put a byte. It's much easier to think about this as addresses increment by 4, okay? And now at location 1AC, you get that entire word. So in this world, it's important to know your endingness, right? And how that transfer is going to occur. And just a reminder, so little endian is increasing numerical significance in your numerical significance is increasing memory address significance. The big endian is opposite. The ISA, Thumb 2 ISA supports both. In fact, there's an instruction. You can just point, run this instruction, and then it'll reinterpret all the commands after that as big endian, right? So somebody else can write some function. I don't know why they chose big endian or little endian, but you have to deal with it. You just write one instruction, it'll switch it for you, okay? In this class, we're little endian unless otherwise stated. My brain can't go back and forth, stuck in one. I'm choosing little endian for now on. All right, so now we have, that was mostly how is memory organized. Now we have registers, so there's 16 32-bit registers for the core. So you got a number of general purpose ones, so 13 general purpose. You got the stack pointer, link register, and the program counter. There are these kind of shadow registers for the main stack pointer and process stack pointer. We're not really going to discuss those. They're not a vital part of this course, although it will come up again when we're talking about interrupts. So that is mode dependent. Oops. We're mostly going to, and then the other one is the special purpose registers here. So these hold the state of the core. So things like what are the ALU flags? What interrupts are active? What's the base priority? If there's faults and stuff. So there's some general purpose registers. We will touch on these, especially when we talk about interrupts, and in a little bit when we're talking about ALU flags. But mostly you just need to know that there are 16 32-bit registers in the core. Any questions? Yeah.
Is there a 0 register?
Is there a what?
A 0 register?
Nope.
No.
If you want constants, you got to put them in yourself. So that we'll talk about that, but you could use like a move command and move in an immediate. Any other questions? What processor has a 0 register?
All the stuff we did in 370 there's a 0 register.
Ah, yes. So no processors. Okay. And then it's just useful to think about how, your C code, where it gets stored and how it's implemented on the hardware. So you have things like, and here's flash memory down here where your instruction space is, and then you have SRAM where data is. In reality, flash is slower than SRAM, so there's a trade-off in speed. While not important for this particular slide, in lab you'll find that they actually take your program out of flash and they put it in SRAM when you boot up, part of your bootloader, just so it can be faster. Right? You do have to pay some penalty on startup, but for most of your labs it doesn't matter. That's just the default about how Cube IDE runs things. Anyway, so then you have your data space. You have variables that are dynamically initiated. So here and here. So this is like if you're using malloc or calloc. Those things are going to come up from the heap up from the bottom. We don't really focus on the heap here. It's not that important for what we're trying to teach. We spend a lot more time thinking about stacks and stack pointers. So there's another place where you can store variables. The stack is mandatory to always keep track of it, and you'll find out mostly because of functions and programs need to keep track of the state, and so do interrupts. Your code will go into flash. And then typically, like one-off, one-used iterators and may never make it into one of your memory locations is most likely the compiler is going to define it to be in the register space, right? Okay, so to recap, we've got registers, 16 of them. 32-bit wide, we have memory. Memory is unified, so you have instructions in memory. Here I just decoded them. And then you have data in other parts of memory, okay? This is 32-bit wides. I think my indexing here is off a little bit. I have to think about that for a second. But 32-bit wide, and then if you're in 32-bit mode, way of thinking about these would be indexed by 4. Okay. All right, so we'll talk about instructions. And we're not going to go through every instruction. It's not possible. We're trying to give you the general layout of how to interpret instructions and what you need to know. So here we have some move S. So move is this an instruction. It's going to take something like an immediate here. So pound 10 defines an immediate. This is in decimal form. You would have to do 0x for hex or 0b for binary. At least that's how we would denote it here. Most IDEs will do that. And now we're going to move 10 into the register R0. But if we want to encode that instruction and figure out what, if we looked in memory, what would that instruction be, we need to go look at the ARM reference manual, and you would go look up the encoding for this structure. So we have move S. And then you would go through and say, okay, here's the immediate. You figure out the binary here. And then you have to figure out what register it's going to go into. So this is register 0. So if you go through. So let's see. This first section is already defined. This tells the core what instruction it is. Then you have this register here. This is the 0th register, so all zeros. And then you have the number 10 in binary. So if you put that all together, turn it back into hex, this is what you would see at that memory location. Okay? And then we can do the next one. Same thing, only thing that's going to change is the immediate and the destination register. So you can go through here. Destination register is 1, immediate is 0. And then where's it going to get stored? It's a 16-bit instruction. So instead of going and putting it on the next 32-bit address, we'll just stuff them together. Okay, so here's where we're going to save some space. Should feel like a review of 370. Great. Just slight nuances for ARM architecture. Okay. So, this is a multi-stage processor. When your PC fetches a word, it always fetches 32 bits, and then it increments the program counter by 4. So it's always just going to take 32 bits. Remember that because it's byte addressable, you want to go to the next whole 32-bit number, so you have to increment your program counter by 4. Okay, so if you go to that memory address, you grab this value, there it is, 2000, blah, blah, blah. That's the value. Then it's your job to decode it. So, it's a 3-stage pipeline. So if it's a 32-bit instruction, it's kind of a standard pipelining thing. If it's 2 16-bit instructions, right, then it's just going to wait. All right, it's going to hold that one, and then it's just going to wait until it's its turn, right? That's pretty easy. You don't have to go and fetch again because you know it's a 16-bit instruction. So the question for you is, if the core is going out there fetching 32-bit words at a time, how does it know if it's 2 16-bit instructions in there or one 32-bit instruction? Okay, talk amongst yourselves. Nope.
I was going to say maybe there was like an extra bit or something somewhere. But, I mean, there's no extra bit. It's using
Specify or something like that.
3 bits. How am I supposed to get 50?
I don't think they're stored in one place. Well, I don't think you can switch between them on this machine. They're both stored in the flash. So you'd like specifies all instructions. Like some of the ARM tool chains, my guess is that.
What do you think? What are some strategies that an architect could come up with?
Something like in the instruction coding it says.
Yep, nothing too magical. So ARMS basically says if these are the beginning of your, at the beginning, so you bring out 32-bit word, if these are at the highest bit locations, then that's going to be a 16-bit instruction. Otherwise, what is it? Oh, it's going to be a 32-bit. Otherwise, it's going to be two 16-bit instructions. So basically, they're just using some basic encoding structure for that. Yeah.
What happens when you have a 16-bit followed by a 32-bit? Do you like fill out the 16-bit with zeros, or do you chop out those 32 bits in half?
I don't actually know. I'm going to guess. We could guess that they would probably just put zeros in there, or maybe they have a no-op command. That wouldn't be very advantageous though, because then you waste a cycle. But maybe they do. But yes, they would certainly have to handle that condition, and we could look in the ARM manual to see what they do. It's a good question. But they would definitely have to handle that condition. They also typically do not allow off indice addressing, so you get a compiler error. So you, for instance, you can't take a 32-bit word if you're not falling on the 4. So memory is going incrementing by 4, and so you don't want to take a 32-bit word out of a increment by 2 address. They'll give you a compiler error for that. Yeah.
So does this mean it's guaranteed that you'll never see those 5 bits like in the middle of a 32-bit?
We're only looking at the beginning, right? So you take a 32-bit chunk out of data, out of memory, and then you're just going to look at the first, whatever it is, 5 bits. And if it's one of those patterns, then you know what to do with it. Otherwise, you're going to assume it's the other type of instruction. But it's not anywhere in the instruction. Okay, so we can think a little bit about some of the ramifications of having different code sizes and what these instructions are capable of. So here we have move. We're going to try, and here I'll try and explain it. So there's move immediate and there's move register. So move a value to send register to another register. There's move immediate that we've already talked about. And there's actually like 4 different encodings of it, but I can just show you here. And so there's 2 different ways to do it. They're basically saying you can have a 16-bit version or a 32-bit version. Okay? So what would you use? Which encoding, T1 or T2, would you use for move S, R3, immediate 15?
I use 160 or 132 and 116.
132 and 160?
132 and 216. Sorry.
I was thinking more, which one of these instructions would you use?
I'm sorry. I'm
No, that's
reading
fine.
this off of my iPad and it already has all the. Never mind. I'm looking at the wrong thing. So.
Okay. So would you use a 16-bit instruction or a 32-bit instruction to encode this?
16-bit?
Yep. Could you do it with a 32?
Yes.
Okay. So the compiler can make a choice, but there's no big advantage to using a 32. Okay? Because you can go get 15, you turn 15 into binary, and you can fit it within 8 bits. So here it says immediate 8, and then there's a destination register. Okay? And destination register is only 3. How about, yep, that's T1. How about this instruction? Yeah.
T2.
Why?
Because 9 cannot fit in the 3 bits.
Right? Perfect. And how about this one? Either this is too easy or too hard.
T2.
Yes, but why?
Because 416 cannot fit in the 8 bits for.
Yeah, I forgot to give you the hint. Hint would have been helpful. But basically, yeah, you can't get this number, because this one extra digit, into there, okay? So that just kind of shows you some of the trade-offs of what you would do, yeah.
Where, let me look at T2 one. It says there's only 8 bits for the immediate. Is that the immediate 3, do they also add?
Yes, these things are horrible to read, and it takes you a long time. So here's what you got: 8 here, you got 3 here, and you got 1 here. Right, and they just put it all over the instruction. That's great. And then how do you know what to do with them? Well, then you have to go through here and you see how they concatenate it. Right, so this tells you that this is the order. So if this is how you can get, what is this, 12 bits into this one, okay? Why didn't they just do it all, just the lowest bits, for instance? Why do they spew those immediate binary values throughout the instruction?
think it's that the register is in the same spot for P1 and P2. It's the same bit.
Yeah, right. So basically, you have to make a bunch of combinational logic, which is going to interpret your instructions and do something with it. And so making custom combinational logic for every possible instruction is painful. This wastes space. So then they run some optimization algorithm that says, what is the least amount of instruction or combinational logic I need to decode all these things? And then they probably come out with a nice set of placement or whatever. I don't know if it's nice, but this is the placement they came out with. Okay, so that's T2. Okay, so question for you. So why does the ISA, and we saw this before, I didn't highlight it, make a differentiation between low registers and high registers? And what does that implication have for 16-bit and 32-bit instructions?
So the first
Yeah, you have to use high.
so it's almost like you have
I can't fit in
16-bit.
a high registration.
Yeah, high needs 32. No need 32.
我觉得就是默契的3个这种。
The thumb part is the 16-bit, right?
Be able to set just
Two is both 16.
High registers have to be
All right, what do you think? Why do they make a distinction between low and high registers?
So those low registers, you could use 3 bits to represent them. And once you go above 3 bits for those high registers, you need bigger instructions. So that's probably where the 32-bit instructions come in.
Yep. So if we go back, just looking here, we see that they're only giving you 3 bits to define the destination register, and here they're giving you 4. There's no mandate that they couldn't give you 4 bits in the size of a 30 or 16-bit instruction. It just makes a division of labor kind of good, right? So 16-bit instructions go for the lower registers. Probably also some backwards compatibility to other ISAs, I don't know. And then if you want to go to the higher ones, then you're going to use probably a 32-bit instruction. Also, if you think about it, probably most computation is happening when those lower registers anyways. You're just trying to add some numbers together. Then if most of your instructions are going to be in the lower registers, just make those instructions smaller. There's no advantage to always using 32-bit instructions. All right. Any questions? I promise I can't be that good a teacher. I know there's questions out there. Feel free to ask them. All right. So we'll talk about some different types of instructions, just so that you have that background of how the ISA is supposed to work, and as we start putting things together. So there's a bunch of algorithmic and logical instructions. So if you really care about exactly what you're supposed to say, so in the exam and for homework I'll do as well. For in the exam, we'll give you a cheat sheet. You're not making you remember how to, like, what an S or a subtract instruction is and how all the operands work is not valuable, right? We have computers for that. I need you to know how to use that information to accomplish a task. So there's no reason to study. I'm just trying to tell you these are things you should be aware of and be familiar enough with that if you were asked to, I don't know, use branching or loads and stores, you should be familiar with these concepts and how to get it done. So, okay, so some common arithmetic operations. Like in all processors, you have add, carry, subtract, multiply, divide, all the common things. One special class of instructions allow you to set an extra bit, and this is the S bit. So the S bit allows you to update, it tells the ALU, update your ALU flags. So for instance, here, while this code doesn't, well, in this particular code, you're loading some words, that's great, and then you have this add S. And so when you add S, then it's going to update your flags here, which can be used later on. So that's just, if your particular instruction allows it, you can look in the manual, then you can go and update the flags. And so these are the kind of standard, is this negative, 0, is it a carry, is it an overflow, is it a saturation? These are just process flags that help you later on in your instructions. So if we look at an example, say you want to add two 4-bit numbers together, okay? And here in this particular case, you're gonna have to have a carry. So there's overly complicated ways I could program that if I really wanted to and keep track of all those sort of things, but having the carry flag makes it easy. So in this particular example, we don't have to dive into all the code yet because you haven't seen what a MNV instruction is, but we'll go through it later. Basically, the top bit of instructions is just setting up those values, the value of A and B into registers. Okay, so R0 is going to have FFF, R2 is going to have 2, R2 is going to have 1, and R3 is going to have 4. And then you do the add, and you set the register or the ALU flags, and then if this instruction here, add carry, looks for that flag, and then we'll take that carry bit and do that task for you. So they will do it correctly by setting that. Now you don't have to set it. You just, I mean, in this example you would, or else it wouldn't operate correctly. You don't have to set it. There's no advantage or disadvantage in the sense. It's just if later on you're going to need that value for something. Okay. There's also bitwise logical operations. I'll show you 2 examples when they're particularly useful. So you can do ands and ors, bit clears. If you want to OR things, so this is a particular value. Say you have a bunch of GPIO pins and they have LEDs blinking. And somebody else has set the status for one LED that says power on. Another one sets the status for wireless connectivity. Another one says the user press the button. You don't want to have to go through and read every single value and be aware of everybody else's code so you write exactly the right thing in. It's much nicer if you can just do a bitwise OR. So you can just take the register that's holding the output state, take that in, take your mask that you want to, the bits you want to add to it. So here I want to add 1 and 1. You OR them together, and now all that information is retained. You didn't have to do any calculations on it. You didn't have to hold the state. You just, all that information is retained, and here you've gone and update one of those bits. Okay, so that's an easy way to not worry about somebody else's code and what they're doing with those LEDs. Likewise, if you want to clear something, so bit clear, here's the effective code of that. Basically what you're going to do is you want to go and clear some bits out of some register. So you say here I want to clear out the lowest 4 bits. This instruction will invert that, and then it will AND those together. So here we're able to take this original string here and then clear out those low bits. Particularly useful instructions just to be aware of. All right. All right, we'll move on. We talked a bunch about moves already. Basically, you have the ability to move things from one register to another. You have the ability to do move immediates. The NVM is a negative. You take whatever the value is and you invert it, basically. You turn all the 1s to 0s, 0s to 1. It lets you generate some high numbers easily. We use it in some of our examples. It's not that important to memorize. There are 2 instructions, or two instructions that are relatively useful to remember, especially for exams, and that is move wide and move top. Okay. So say I have R0 is already initialized to 0, 0, 0, and I want to create a 32-bit number. Remember, I can't take a 32-bit number, fit it in an instruction, and put it in a register, because I won't have enough room to define what the instruction is and to have the destination register in it. So you're going to have to do this in 2 operations. So here's what we're going to do. We're going to say move wide, and what it's going to do is it's going to take that 32 or that 16-bit number, so 4, 3, 2, 1, and place it in the lowest registers there, and lowest bits of that register, which is R0. Then you can move top, and move top does a nice thing where it does not affect the lower bits. Right? So now I can just put the top of that 32-bit number and the top 16 in, and now I get 8, 6, 7, 5, 4, 3, 2, 1. Now, the nice thing here is that those lower bits are unaffected. This is not reversible, though. So if you go the other way, if you did move top, let's just say this was unknown up here, you would rewrite the top of R0, but then when you come and do move wide mandates that there's zeros here. So now you're going to erase what you did for the top, and you'll come out with 0004321. So these are not immutable. You have to do them in the correct order. But it's a nice way to get variables into registers quickly if you're just writing sample code for yourself. Yeah?
So move y twice in the first example would effectively write 8765 in the right 4 bits.
Yeah, so if this up here was move y twice, you mean?
Yeah.
Yeah, then it would just be, it would come out with 8765 in the lowest bits here. And this would be high, or this would be all 0 if we change the code to do that.
Why didn't they make an instruction that just does both of these?
How would I tell the processor what to do? So I need to tell the processor, here's a 32-bit number, and I want you to take this 32-bit number, immediate in this case, and put it into a register. So how do I have enough code space to define what that 32-bit number is? I need 32 bits for that, and I need to have a destination register. So now we're at, 35 bits at least, but my entire processor is only 32 bits wide. All right, so we have this limitation with our hardware. We have things that we want to go and compute. You want to do immediates, you're going to have to do it in 2 steps. It's a good question. Any other questions? Yeah.
Why do they make it so that it zeroes out the half word?
Why does move W zero out the top? Well, move is just a variant of move, right? So if I want to move an immediate, I don't want, and there's some data that was in that register, I don't want that leftover data there. Right, so I want you to move 4 into this register, and now you come up with 87, or some thousands of numbers, right? Well, I don't want some old data in the top of my registers. Does that make sense?
But you want data in the bottom left of the register?
Say my goal is I want to instantiate, maybe I didn't make this clear, I want to instantiate a number in R0 8765431. Okay, how can I get that number into that register?
What you call move W, then move T.
Correct. That's one way to do it. So what's your question? Sorry.
My question is just like this tool is just like a design question. I just don't know why they designed it. That's
Okay, that's a good question. Alternatively, how would you design it? Put it back on him, you see?
I would design it so that it doesn't zero it out, because it doesn't make sense for one command to zero out and then the second command to not do that.
Okay, that's fair. You could totally make that. And then we can make a separate instruction. Maybe it's called move Z, move zeros, right? And then those smart folks at ARM would probably look at all their workloads, right? Because that's how you figure out what instructions you need. You send your workloads through your simulator, your architecture simulator, and you say, how often does this have? And I bet they said, R0, our invented code, doesn't come up that often, and I don't need it. So you totally could do it. It's just that they have chosen not to do it. All right.
The questions are clarified.
Real loud.
Just the questions are clarified. So if we do like a move W with a 5-digit hex, we're gonna lose the most significant digit, right?
No. This is an immediate. Okay, so the immediate can only be up to 16 bits. Say you did a move register, which would be a different, not a thing, then it would move the entire register. So register 0 to register 1, for instance.
So you're saying we can move a 16-bit immediate, but in the encodings we looked at, there were only 11 or 12 bits dedicated to it?
Correct.
So where are the other?
We did not look at all the move immediates that are possible. There are lots. So yeah, I mean, we could just look in the instruction set, it'll tell us what's available, yes.
What's the difference between an immediate and a constant?
I don't think there's any difference.
Oh, okay.
Building off that, I don't understand what the difference between, because you have to use move Y first before using move top.
Correct.
So why wouldn't I just use move with a 16-bit number,
correct,
then move top?
You totally could. Move W is just the dot W. The W just instantiates this must be a 30. You must use a 32-bit encoding.
But like,
This is
couldn't you just get rid of that instruction? Because in every case that I use move W, I could just use move.
move W. Well, okay. I don't think I can put a 16-bit number in a 16-bit instruction. Okay. So I'm just thinking out, and you're not wrong, because this is the intricacies of how the assembler works. So you would go through and say you try to write assembly that said move a bit that's larger than 16 bits. It will go and choose, the assembler will choose to use a 32-bit encoding for that. Because there's multiple ways that we saw from the move S before, depending on what numbers you put in there, that gives you different encodings. So I guess I should have clarified that move W and move could both be 32 bits. Move W just defines that is going to be a 32-bit instruction.
Move would otherwise cut it?
No. Move is just move this immediate value into this register. It'll pad all the zeros up there. I've thoroughly confused all of you. Fantastic. Professor job achieved. Yeah?
So does regular move,
Really loud.
regular move doesn't zero out the first top 4 bits, right?
Correct. It's gonna,
But they're effectively the same thing apart from zeroing out, right?
oh, sorry. When you say zero out, it's going to put the number immediate in there. So those top 16 bits, I misspoke, those top 16 bits are part of the number, right? So it's not that it,
It will be zeroed.
yeah, it'll be zeroed out,
So if the
sorry.
number is, because its limit is 16 bits, the top 16 bits will be zeroed out.
Correct.
So it's the exact same thing as move W or no?
Yes. Except for a small nuance, which you may experience in your assembler. Yes. I can just modify that slide. I can just take that out, and you all will be happy. That's fine. Less confusion is good. What slide number is it, 60? Okay. Are we done with this cursed slide? All right, the big takeaways. Don't worry about move W, move, okay? You just take a number and you put it in the register. Whatever that number is, it goes in the register. Move T is the special case. Move T only affects the top. That's the takeaway, okay? How do you feel about that? I can tell you like, don't believe anything I'm saying at this point.
I just don't understand why the documentation is different. If it's like why is it const and immediate 16 if that's the same thing?
I will go and enjoy the data sheet tonight, a couple thousand pages, and I will hopefully come back with an answer. Okay. All right. Any other questions before we go on to other confusing slides? Okay.
So in the homework, should we follow like ARM instruction or ARM like V7 instruction?
We're going to use the ARM v7m architecture, and you should always use thumb 2 instructions. All right, so now we talked about move, and you can move from values from one register to another register, or you can move immediates. Load and stores are instructions that get things out of memory for you, right? So now we're going outside the core, we're going into memory, and so here we are going to say that we have load R3 brackets R1, so we're going to use the value stored in R1 as the address to a memory location. And I always remember the brackets are giving me that idea that's a memory location. So it's the value in R1 points to the memory, and then it's going to take that value and stick it into R3. So basically I'm just going to load some memory or some value into my registers. And then there's a whole bunch of encoding for that, different encoding styles for immediates or for registers. Now there are lots of different versions of load and store because of the design choices the architects made about how memory is laid out. So you can go do kind of standard, load a 32-bit word, store a 32-bit word. We're not going to worry here about privilege and unprivileged and exclusive. It's just beyond the focus of this class. They also give you things like you can store a 16-bit word You can store, you can load unsigned, lone signed. You can do an 8-bit byte store, 8-bit load. And so if you think about that, that kind of makes sense if you think about how they structure their memory. Because if you want to do a byte operation, you want to just get a byte out of it. You don't want to have to pull out a whole 32-bit word and then throw away the top, like do a bit clear, just throw away the top bits. You just go and use this load bit, store bit to grab that particular word out, okay? Or sorry, that particular byte out. And again, you can also do that for 16-bit operations. So for instance, and the other one is if you're loading information, right, and it's a 16-bit, so this is a load signed half word, that's what this instruction is. What do you do with the upper bits, right? So if you give it the command, I want you to have this be signed, it's going to fill in, sign extend the top bits, okay? How do you feel about that? That's causing questions. I can feel it. Okay, then I got you now, ready? Why, if I can do a load signed half word, why is storing a signed half word not valid or useful? All right. Well, I'll let you guys talk about it for a minute. Have a minute.
The point of storing a half word is
byte addressable, right? Whereas registers are like something else. So if you want specific numbers in a you only want to like have
Storing a sign.
the sign extend that, or else like it could be the different number. Whereas in memory, like they still call 64 bits a double. Sign extending something 64. Makes sense, yeah.
So whole register is a full
You can't like load two values because it's technically each
All right, what do we think? Why is this not useful or valid? Or am I?
register.
Think.
Storing a larger version of the same number, which is like redundant or something.
True, you don't want to go and override this memory up here, right? You don't want to go and put a assigned 8-bit value in here and then have it extend into these other memory locations. That would corrupt that memory, right? If you wanted to overwrite that memory, you should have used a store word to do that, okay? So that's a statement about, why does it not even matter why are there no signed store functions?
When you load, you sign extend, so the value is correct.
Yep.
Then when you store, if you sign extend, like it's already sign extended.
Yes.
The point. So.
And the other idea, there's no type in memory. There's no typecasting, right? So your SRAM does not care if it's signed or not signed. There's no idea about that. You as the programmer, or at least the compiler, has to keep track of that and say, oh, that thing I put in there, that's 2's complement. I got to go and treat that special. But the memory doesn't need to know anything about it. So telling it that using a special function or instruction that stores it signed, memory doesn't care. Just give me bits. I put bits in there. That's all it does. How do you feel about that? Okay. A word of caution, because I got confused when I was making that example last night, that how your ISA or how the slides represent memory matters. So here, and let's see, in this example, addresses are going up, okay? And we're reading an entire word like that, word at a time, at least in this example here. So these are two same versions of memory, right? So this is looking at a word at a time with your address incrementing by 4. This is byte at a time, address incrementing by 1. If you go into your IDE, this is memory addressed by bytes. So here I put in 8765431 into memory. And so given by our last example, this would be the word representation, but it changed the word order around in the IDE if I did half word and by byte because of what it considers what's the next bit or what's the next address, right? So you can see here that they've swapped it a little bit. So you just have to keep track as you're going through homework. You're looking at exam questions, you're using your IDE. Big questions are, is memory going up, is memory going down? First thing you should figure out, because turns out I'm not always consistent on those exam questions. Just fair warning. And then make sure you understand how is this incrementing by 1 or is it incrementing by 4? So you can understand the layout of the memory. I will try to keep it consistent. I'm just not infallible either. All right. All right, so we're getting a little long, but we're getting there. So one of the big ideas with loads and stores is how we can do some offset indexing. So you have oftentimes functions that iterate. I want to go and place things in memory with a particular offset. Okay? So they've given us functions for that. So you can have normal, place it in a thing. You have offset indexing where you say, place it at this address, plus 4 plus some number. And then you have options to do the indexing before or after you've done the load and store. So we'll walk through some of those examples to make it more clear. So here is just a normal vanilla load instruction. And store obviously works the same, just in reverse. So here we have R0. It defines the address in which we're going to get data from. And then what are we going to do? We're going to go place that into R1. So here we're going to use R0. We're going to look at that address, and we're going to take out, this is a 32-bit operation. It's not LDRH or LDRB, right? So we're going to do a 32-bit, and we're going to grab, remember, so this is, in this example, memory is increasing upwards, and we're incrementing by 1. So we're going to take 32 bits. We're going to take that, we're going to go put it in register R1. Okay? Questions so far? Great. Next, now we're going to do offset indexing. So what we're going to do is we're going to go into R0. That's going to be the address that we're going to get data from. But on the fly, as we go, the core is going to add 4. That's the offset. Okay? And it's going to go and increment the memory location. So you, as a programmer, don't actually have to go and, or the compiler does not have to say add 4 and keep track of that. It just says, here's the instruction, just do 4 offset from that. So you do that on the fly, you grab that, and you go place it into memory. Okay? And you might be saying, why did I write dead beef? It's because old computer people, man, I don't know. This is this like classic hex games that, boring engineers play. You can spell things in hex. That's the best we got. All right. So you do that on the fly, but we're not going to change the value in R0. We're just going to say, for this one time and one time only, we're going to take this value, we're going to add 4, we're going to pull back data. So pre-indexing has this bang at the end. And the bang, the explanation point, for me, it says do it right now. Increment the index right now. So here's what we're going to do. We're going to go take this value. We're going to add 4 now. We're going to change the value in R0, adding 4, and then we're going to go get the data. So we've increased it. Now they essentially do the same thing. This in the last example. The only difference is that now this register has a new value in it. So this updated, this kept track. This is holding the state information of where we got that data from. And then post-indexing, this is the non-bang version, so not right now. Go out, get your data, okay, bring it back. We're just going to go to the location defined in R0. We're going to put that in R1. However, after we're all done, we're going to go and increment by 4. Okay. So this is just like you're iterating for for loops. I don't know why. They really wanted us to have this functionality. And they're making the ISA. They said, man, this is really important for us to have. But it is important to think about how when you start doing things like setting up peripherals, you're going to have things like base registers, and then you're going to have the offset. So it's like port A on your microcontroller will define how these GPL works. GPIO works. Port B does exactly the same thing with different pins. So now you can use exactly the same code and just all you have to do is change the base address, and then all the incrementing will allow you to do the same functionality on either side. So there's good compiler reasons, good code efficiency reasons why you'd want to have this. Any questions? Yeah.
For the second example,
You want to go back? Is this?
I got confused a bit. Did we change like the Indianness and Indianness of
No.
the operation?
I don't think so.
Because one of them went above. Were they two different operations? I might have missed.
Well, we have 3. So we have vanilla, or no, we have 4. We have normal, offset indexing, pre-indexing, and post-indexing.
I see the mark right now.
Okay, great. I solved one confusion today. I nailed it. What other questions do we have? Yes. Real loud.
So I'm assuming there's just different applications of indexing or not indexing the address at R0.
Yep.
I don't know if this one's asked for an exam.
What's that?
An example of like
why you would want this? Why in the world would we do this? Is that the question?
Post index versus pre-index or not index at all.
I kind of think like you're going through a for loop. And sometimes you want to index from 0, sometimes you want to index from 1. It's just how you construct the problem, you want to have different functionalities. That's it. So you're absolutely right. We could probably do this. We could write the whole program would just load and then mathematically keep track in the registers of what the next address is. It just helps us make more efficient code. That's it. Yeah. Yeah.
I'm having trouble understanding like pre versus post. Like, can anything happen in between like the instruction? Like, why does it matter if you increment it before or after?
It's just it matters which address you're going for, right? So if we do pre-indexing.
Oh, okay, I understand.
Yep, so just, okay, good?
Yeah.
Yeah.
Earlier slide, can we go back to the diagram that shows by word, by half word and by one after this?
After this. Yes.
So why for half word did it get switched around?
Because this is just warning. This is not something you have to keep track of. Basically, it said that, let's see. So here is 0, here is 1, here is 0 or 4, here is 5 or 65, 66, 67, 64, 65, 66, 67, okay? Here, it's just 64. Right? So it's like, how did this particular representation choose to index these things? They didn't, it would have been really nice if they just made a whole line, right? And then they would have an explicit mapping between whatever this is, 65, right? But they didn't do that for you. And it causes problems every year.
It's because of our end uses that we
Yeah. Or at least how implicitly they're putting numbers, like the sub addresses that they're not showing. So it's just a warning to keep track of that. It's a little bit of pain. Yeah.
Is there like different applications for each endianness, or do 2 just exist for like no good reason?
Man, this is even before my time. I don't even know. Is there? No, there's no inherent. I have not gone deep enough on the internet to figure out why you'd want one or the other. I feel it's probably a cultural thing. Depends which part of computer science you're from, but they both get the job done.
Yeah, it just like little onion kind of seems backward because now like the 8's next to the 5, but just me, I guess.
I'm just pointing out the problems. I can't solve them.
Does the endianness only affect it when you store, and then when you load it, it just takes like the smallest memory and puts it into the, or like it only affects it when you store and not the load?
It will affect both, and we're just going to assume it's little endianness. If that helps. All right, we're not going to get through the example today, but I want to get through a few more slides, which is fine. Okay. I'd rather have good conversation than blast through a bunch of slides. This doesn't matter. It's cool. I'll just tell you what the answer is. There's like, what's the biggest offset you could do? And then you're like, well, which means like, how far away in memory can you jump? How far away can you grab data out of this thing? And basically, it's just whatever your immediate size is, and it happens to be 4 loads, and it's going to be 495 indexes away, or 4,095, sorry. All right, so let's talk about flow control. So branching. So there's branching functions for program execution. So we have this concept of labels. Does anybody know what a label is? You guys cover this? Okay, thank God. I mean, it's been like 4 years since I taught 370, and I've also dumped it all. Okay, so we have labels. Labels are locations in memory that get defined when you compile your code or you assemble your code and do floor planning. We'll talk about that later. So you can branch to a location in memory, or you can branch to a location defined by a register. The trick here is the extension of L. This defines that you're going to load the next instruction into your link register so that when you go off and do a program or a sub-function, you know where to come back to. Okay? Pretty basic stuff. There are a bunch of conditional flags that can be sent. Again, if we look back at the program status register and setting those S flags that can get set, you can look at those and do certain code operations. So you can do branch if equal, branch if not equal. Okay? And so now you can concatenate all those conditional codes with your branch instructions. Okay? So you can branch, if sign less than equal to 0. Not sure why you'd ever want to do that. I'm sure the compiler knows, but it's an option. There's also functions to do this explicit just functions that just set the compiler flag. So you have compare, test, all those different things. What's interesting to me, at least, is that these conditionals work with almost all the instructions. So you can load if equal. Just saying, it's possible. So now you get to make more complicated and interesting code flow based on, will you branch? Sure, but will you even load code if the last thing was equal to 0? And normally that doesn't really matter, but I had one case in my research where it made a huge difference. So at least being able to access those flags. So me and my buddy were working on that WISP project, the RFID tag that had no batteries and ran a full microcontroller. And what we had is a very challenging timing constraint where we had a bit stream of data coming in, so basically edges, and we had to count, like is it 1 or 0 on a certain time frame, and we just ran out of, we had eight 16-bit registers, that's all we had. We ran out of room. We didn't have enough time to store it into flash. We had to keep bit control of one piece of information. So what we did is we just repurposed one of those flags. I think it was the equals flag or 0Z flag, and we just rewrote it to keep a little bit of state. And so there we found an instruction that will allow us to set it, and then we had a conditional that will allow us to continue with our code if that thing was set or not. So anyways, just a trick. If you really had to, you write an assembly, you can reuse even those flags for your own purposes. It does not have to be as the ISA intended. Okay. I have 3 whole minutes. Fantastic. We're going to do a very basic example, try and bring it all together for you, okay? So we're going to run this code, we're going to load things, we're going to add things, and we're going to store things. All right, so here we are, let's see. The program counter is pointing at 1AC, so here. So we're going to go and we're going to fetch that value out, okay? It happens to be a load, load the address that's stored in R0 and place the contents of memory into R1. The value in R0 is 2000. Again, this is all unified memory, or not 2000, but 200000. Okay, so now we go and do that task. We're going to go take that value. We're going to go put that in R2 or R1. We're going to put the value 2 in an R1. Next, we're going to go through. We're going to increment the counter. So it was 1AC. We're going to increment the counter to 1AE. We're going to go and fetch the next instruction. Magically, right? It's been decoded as add the value 1 to the register R1 and store in R1. So now we've incremented the value to 3. We increment the program counter by 4. We fetch the instruction, decoded it as store the value of R1 into the register defined by, or the memory location defined by R0. And there we go. Okay. Great. And we'll do the exercise next time in class. All right, thanks.
It's two bytes is 16 bits? 2 bytes is 16 bits.